Okay, in the next installment of the METOS videos, we'll look at disease models for wheat, and including barley. So like every other disease, there's a number of biological factors of the disease. So disease development or the fungus depends on the environmental conditions. It's assumed that the host and pathogen are present at the same time in your region. Plant disease results only if all the factors do occur. So if the disease is newly emerging in the region, the inoculum levels may be too low for that pathogen to cause a disease outbreak. So the disease triangle really shows this. We have the pathogen, the host, and the environment. The environment being the conditions, temperature, humidity, precip, leaf wetness, tip the scale in favor of the pathogen to overwhelm the natural defenses of the host, which leads then to the cycle of infection on a particular cereal crop. Again, we need environmental data at the field to do this, so we need to track things like temperature, humidity, leaf wetness, precipitation for this particular model for Fusarium head blight. So the importance of localized weather data can't be underestimated. In this example, we're looking at two weather stations, only 1.5 kilometers apart, one at a main office and one actually in the field, and we can clearly see the difference between the model for these two stations. One shows a very good, strong response to disease development in the field. The other is much weaker under a grass environment. So the microclimate at the actual field does impact the model's sensitivity to showing the degree of risk. So you need to design a network of stations based on your fields or customers' distribution, the geography, and the placement in the field. We can't use weather stations that are 10 kilometers away from a particular field to make a valid assessment of the disease risk at that particular field. So in terms of the wheat production system within Fieldclimate, we have a whole number of different models, I think about 14 different models. Today we're only focusing on two very similar, Fusarium head blight and a Fusarium head blight risk, but we all know it's the yield and genetic trait sets the yield of a particular harvest, but it's the impact of these diseases and pests and so forth through the year that really affects the yield as well as the quality of the crop. Especially with Fusarium, we'll see the impact on grade from it. So the model proposition for wheat diseases, in particular Fusarium, is very strong. It's a very detrimental disease in Western Canada. It affects many cereals across the country. Meteorological specific sensors support then, in-field sensors, the conditions for spore infection, the mycotoxins, and the FHB risk. What that does is allow us to time fungicide applications based on the growth stage as well as the disease risk pressure to preserve, in this case, yields and grade. So we want to know the synchrony of the crop in relation to the actual disease risk pressure, mycotoxins, and infections. What we're doing then is preserving yields and quality, which is our value proposition, and becoming efficient in the management. So we see the whole cycle that can go on in terms of the overall development of Fusarium within a particular field. It can be carried over in trash and other crops, and spores released and infected at anthesis, thereabouts, on a cereal crop such as wheat, and you get an orange tinge to that mass if it's severe, and then causing obviously problems with yield and grade. So the Fusarium models in Fieldclimate are really twofold, but they really work on similar principles. In much of the literature, it's been shown that warm temperatures, 20 to 30 Celsius, and long humid periods, so that can be defined by things like relative humidity above 85%, such as this graph, or leaf wetness periods, how long the leaves are wet, will impact the development of this particular disease. So what it's saying essentially is get warm temperatures, you need less hours of high humidity or leaf wetness for the development of the degree. So in our case, in Fieldclimate, anything above 85% humidity or long leaf wetness periods will progress the infection levels or risk quicker. So the two model approaches in our system, one is based on temperature, RH, and leaf wetness, one model. The second includes those plus a rainfall event. So the infections are started based on a 2 millimeter rainfall event. So the Fusarium head blight infection can be assumed if the infection progress value reaches 100%. And the two approaches are slightly different, as we'll see in the next slides. So the first model, the Fusarium head blight risk, has two things. It looks at infection events, which are defined by the green line in the screen. And as those events begin and increase, we can see the risk begin to increase as well. So we need infection events, which are driven, of course, by high humidity, optimal temperatures, and leaf wetting period. No precip in this model. And so a fungicide application should be taken or applied during these high risk periods at the right synchrony of the crop, of course. The next model, the Fusarium head blight model, really looks at the infection events and how this drives the myotoxins within the particular disease. So you need, in this case, high humidity, long leaf wetness periods, a rainfall event to start it, and optimal temperatures, which will then begin the infection process. So you can see this one's a little bit stronger of event at the same time. So we have 100% infection, which leads to a myotoxin event that gets up to 30 or 40 points. So we have optimal conditions once we reach 100% in terms of the infection. And further on, then the model is calculating the myotoxins, and it's really governed off of longer leaf wetness periods. The higher the myotoxin risk will be based on that. So if a rotation, of course, it's management as well. If you have a rotation with other Fusarium crops like corn, then your curative measures should be taken at a lower risk level. So it's your comfort level on which risk you want in terms of the infection level. Are you happy at a 50% where you put an application, or is it higher or lower dependent upon your field management and previous history in your fields? So the impact on Fusarium is quite high on a crop in terms of the cost. It does impact, as we said, the grade, in particular in yield, but more so on the grade. So in Canada we talk about FDK, or Fusarium damaged kernels, and we measure it on a percentage by weight. So there's tolerance levels for number 1, number 2, number 3 and feed of FDK by sample weight. There's been a documented small decrease in yield, but the main economic impact, of course, is downgrading to a lower grade. So with disease severity levels varying between 0.5, 1.2 and 2.2, downgrading of Canadian Western Red Spring, or CWRS, from 1 to 2 or 1 to 3 or 1 to feed on a 55 bushel acre crop has shown, and these are actual stats from Western Canada, that it could cost anywhere from $12, $35 to $100 of lost farm income per acre. Quite substantial. So on a 50 bushel crop, if you lost $45 an acre, you're talking about a substantial loss of money, $45,000 income on a 1,000 acre crop. So if I spent $3,000 on my IoT device for a year, I'm returning more than 10 to 1 on my return of investment for that particular IoT device to provide you the precision field forecast for Fusarium development risk, myotoxins, and infections. So the benefits are, you know before you go, you save time and money to those fields. You verify field weather conditions because you have devices in that field. You have a verified model of infection and risk. You know the verified severity of the infection. You can determine your spray based on the date and hour from the model, as well as a spray cast model we have in addition to that. And you have a past record of infection levels and weather conditions that you can go back and look on. Thank you.